So as you start to use the microscope and you get used to how it feels and how to use it and the fact that it's inverted and everything moves in different directions, one of the other things we need to talk about is basically how big is the object that we're looking at. So in order to do that, we can estimate this pretty well by figuring out how big our field of view actually is. So in procedure 2.3 in the lab, you are actually physically going to be measuring this field of view. So we're going to hand you what's called a stage micrometer. This is basically a teeny tiny little ruler that is about 2 millimeters in length. So you're going to focus on this teeny tiny little ruler and you're going to try to measure how big 4x is, 10x is, and then our 40x objective, right? And we're worried really just about the diameter to give us an idea of how big this is. You're not going to have to figure out the area of the entire thing. We are not going into that level of math here. We really just want to know approximately how big it is. So what you'll find when you actually focus the scope is that when you focus on 4x, the ruler is not going to cover the whole distance. It's really hard to measure because of that. It's like you would have to like line it up and then move it, and it becomes very challenging. So I'm going to say do not use the stage micrometer to focus on 4x. You will have to get it into clear view and focus, but don't use it to measure, I guess is what I should say. All right, so get it in focus on 4x, but do not use it to measure 4x. You will not be able to accurately do that, but you can at 10x. So as you zoom in, what you'll be able to do is line up the end of your stage micrometer here, and you'll be able to count basically how big this is by using the ruler. Now then, when you go to zoom in on 40x, you will also find that challenging because it's so small. You're not going to be able to accurately measure that as well. So you are going to measure 10x. That's what you'll do when you fill in the table 2.1 in your lab book. You will only be measuring the field of view diameter for your low power at 10x, which is the gray boxes in that table. You will not be measuring 4 and 40. Now you still need to have a value for 4 and 40. Okay, so you can't just leave it blank, right? You have to have a value. So what you're going to do is actually use a little bit of math, just a teeny tiny bit. Remember, because our microscopes are parfocaled and par-centered, they are proportional to one another. All right, so they are relatable, which means we can use a really simple proportion equation in order to figure it out, right? So you're going to use the diameter at 4x to calculate the 4x and the 40x field of view. Now we're going to start by doing this in millimeters. All right, so you would physically just go through and count, right? So if this is 1 millimeter, that means each one of these lines is 1/10 of a millimeter, right? So this is 1 millimeter, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and then a little bit. So the way that I have this measured right here, which is not perfect to what your microscope is in the lab, you will have a 1.6 millimeter diameter. So once you have that, you can actually use the equation to calculate 4x and to calculate 40x. All right, so let's look at that equation. Now I will say there is a math video in this playlist that will walk you through how to do the math specifically. So if you are feeling a little insecure about your math skills, watch those videos so that you feel a little bit stronger about the math. I'm really just going to run through an example here of how this works, and then you can watch those math videos in order to feel a little bit more confident. And also practice, right? You can make up problems. Your instructor may give you problems. You can practice with this. So this is your equation that is listed in procedure 2.3 in your lab book. So basically what we find is that there is a relationship between the low power and the high power. So if we want to figure out what our 10x objective converted to 40x is, your 10x would go on the left and we would calculate 40x on the right. If we need to figure out 4x, it is the low power, right? And 10x would then be the higher power. So let's talk about these variables. So FOV remembers field of view. So this is the diameter of the field of view at the lowest power. then the magnification here is the total magnification. So remember, to find total magnification, you have to multiply your 10x times whichever one you're using, right? So if this is the 4x, it would be 4 times 10. So your total magnification would be 40. Then on the other side, we have the same thing, but for the other objective, whatever that objective is, right? So this is your field of view at the higher objective. And then again, the total magnification at the higher objective. So let's use the example of a total magnification at the low power. So in this case, we're talking about our 10x. So 10x times 10 is 100x. Now, I made up a number for us to use. If the field of view at the low power is 2 millimeters in diameter, then we can figure out the other two. So how do we do that? First, we have to figure out what the magnification is of their objective. So in this case, we're looking at the high power, which would be 40x. All right, so 40x times 10 would be 400. So we just set this up in the equation, right? We plug in our field of view, our magnification, and then our other magnification. This field of view will be the variable that we're going to solve for, right? Just simple algebra. So this would be your x value. Now, because we have lots of x's, I usually use a y here because it's easier. So in here, I just typed in that that variable. So 100x, this is the magnification at 10x. Then the field of view, which is 2 millimeters at our 10x, is set equal to the field of view at high power times its total magnification, which is 400. So we multiply that out. Right? And then we divide by 400, right? So do your algebra however you do your algebra, right? I'm doing it the way that I would set it up, right? You do the left side first, and then you get your field of view on its own on the right, dividing by 400 on both sides, and then you would take 200x divided by 400x, which would give you 0.5 millimeters is our field of view. So at 40x in this example, our field of view is 0.5 millimeters, where the 10x was 2 millimeters. So in your table, table 2.1 in your lab book, you will notice that there's another column there. That column is to convert things into what we call micrometers, or sometimes people call it micrometers. So micrometers, or this notation, is the weird little U. Instead of mm for millimeters, it would be a for micrometers. Now the conversion from micrometer, or from millimeter to micrometer, is pretty simple. It's a factor of 1,000, right? So if you remember anything about your metric system, right, this is a pretty simple relationship between the units in that system. So in R, we know that 1 millimeter is equal to 1,000 micrometers. So in order to convert the 0.5 millimeters from millimeters to micrometers, we just have to multiply times 1,000. So we multiply times 1,000. That means that the field of view at high power is also 500 micrometers. So it's either 0.5 millimeters or 500 micrometers. This is the same unit, or certainly the same unit. It's the same number. It's the same measurement. It just is in different units, which sometimes can be beneficial, right? One can be more beneficial to use than the other. So for your math preparation for this lab, and for your lab quizzes, if you have them, and your lab exam, you definitely have, then you should be able to do this, right? You should be able to calculate the field of view when given one of the fields of view, and you should be able to convert that into micrometers, right? So again, practice this, make up numbers. Again, your instructor will likely give you some type of practice problems to help you out with this. So ask them if you don't see that. So then the other thing that we can do with this, which is really quite important as we move into lab 3, is to figure out approximately how big items are we're looking at based upon the measurements that we just took. So if you can know the diameter of our field of view at a certain power, then you can calculate the size of the objects that are in there. Now, this is not a perfect calculation, right? Because oftentimes the objects that you're looking at are not perfect, but it does give us a good idea, right? So this is an estimate of approximately how large the items are inside. So in this example, right, we are looking at the field of view at 10x. So at 10x in this example, our field of view is 1.8 millimeters, right? So you can see our our ruler, it goes out to 0.8 here, so this is 1.8 millimeters. Now, in that same field of view, we look at a slide that has cells on it. So let's say we're looking at a plant. So this is the plant cell wall. All right, so this is the distinction. You have 1, 2, 3, and 4 cells. So if you can see that they all 4 fit there, then they take up approximately the same amount of space. You can take that field of view of 1.8 and divide it by however many fit. In this case, right, each one of the cells takes up about a quarter of that 1.8 millimeters. So you can take the 1.8 and divide it by 4, and that gives you the approximate length of each cell, which is all we're really looking for, right, is an approximation of about how big this is. In this case, they're about 0.45 millimeters long. So again, we're estimating by dividing how many cells would fit. So this is something you're going to find really useful when you go into your cell lab in Lab 3. Now, the other thing you're going to practice in this lab in procedure 2.4 is actually looking at the depth of field. So you will get another slide. This slide is going to have a bunch of silk threads stacked on top of one another. So you're going to see most of them, again, they're not all the same. So you will be comparing how clearly you can see all the threads versus just one thread at a time. So remember, as magnification increases, as we talked about earlier, then the threads are harder to all see at the same time, or at least all see clearly at the same time. You can see one clearly at a time, and as you play with the fine focus, then you can actually see more of them, but you're not seeing them all at the same time, right? You would see the red one, then the blue one, then the yellow one. So you can see one object a little bit more clearly. So then after you have completed your investigation, your stage micrometer, your measurements, your math, then looking at your depth of field, what you have to do is clean up your microscope. So procedures 2.5, why am I reading those backwards today? 2.5 and 2.6, you're going to learn how to put your microscopes away. All right, so it is really important that we take good care of our microscopes, that the cords get wrapped up well, and that we clean all the lenses that would have exposure to us, right? Our fingerprints and oil on our skin can be damaging to the lenses, so it's important that we clean them. So you will see in the lab you have lens cleaning papers and you have solution that you are going to use to wipe off all the lenses. Please do use those lens cleaning papers or tissues and not paper towels or something, because the paper towels can also damage the lenses. So be really careful, clean everything really well, and then set it so that the microscope looks it looks tidy. All right, so there are a couple things that you should do. One, the stage should be lowered, maybe not all the way down, right? And again, be gentle when you do this. Moving the coarse knob can damage the scopes if you move them too quickly. So be gentle, lower it down. And then the 4x objective should be the one that's facing down, right? So be really careful to do that so that the next person that uses the microscope pulls out a clean, ready to use microscope. Be very gentle. The other things in our lab is you will actually see on the bottom, on the side, like right in here, there's a little sticker with a number on it. So in our lab, you'll want to put your microscope back in the numbered slot. So again, it's organized, we know what's right. And then honestly, when we have problems with the microscope, it's very easy for us to talk to each other and to talk to our lab tech and say, hey, this microscope number 8 is not working for this reason. And then the tech can actually go find it a whole lot easier. If it's not organized, then it's really more challenging to do. All of our microscopes also have a dust cover that should be on top of it whenever stored to help protect and keep the lenses for as long as we possibly can. So again, microscopes, it's going to take you a little bit of time, right? They take a little bit of practice to get used to, and I'm going to encourage you to try to keep them as clean as we can so they can last for as long as they can. But they can be really, really helpful in viewing small things, and they can be really cool, especially when you get to view some of the live specimens in the labs.